All right, so this is going to be your lesson 22 instructional video. In it, we're going to talk about the basics of logarithms. First, by answering what is a logarithm and how do they relate to exponential functions. Then we'll talk about what are some of the properties or the laws of logarithms, so to speak. And then we'll get into how we apply them algebraically. Okay, so before we get going, let's review a little bit on the laws of exponents, because to understand logarithms, you first need to understand exponents pretty well. Right, so here's some examples. Okay, so first, let's write out the laws of exponents. So the product law, so if I have x to the a times x to the b, right, this would be equal to x to the a plus b. Okay, so let's keep that in mind there. Quotient law, and I'll do this here in a different color. So if I've got x to the a being divided by the same x but to the b power, this would be equal to x to the a minus b. You subtract the exponents. And go ahead and erase and give myself some more room. The power law. Okay, so the power law, or the power to power law. So if I've got x to the a, and that's all being raised to the b power, that's going to give me x to the a times b, right? And one more law that I left out, which kind of relates to all of these, would be the law of radicals, namely, so if I have x to the a and I'm taking the b root of that, that's equal to x to the a divided by b. Okay, so that's the law of fractional exponents. Okay. I don't think we have any examples of that, but it's always good to keep that kind of stuff in mind. So here we've got x squared. I'll do this in yellow. X squared times y to the negative 3 times xy squared. Okay, so first we want to look at things that have matching bases. So x squared times x, well, that's x to the third. Then we're looking at our y's, right? And of course, we're invoking the product law, right? So y to the negative third times y to the second, well, that would be y to the negative 1, which is going to give me x cubed over y to the first power. Okay, and another quick review, quick reminder, if I have a negative exponent, that's always a reciprocal, right? So for example, if I have x to the negative a, this is equal to 1 over x to the positive a. Okay, so negative exponents tell us that there's a reciprocal there going on. Okay, let's look at another example. Okay, so 2 to the third, all being raised to the second power. Well, this is the power to power law, right? So I'm going to multiply the exponents here, because that's 2 to the third times itself 2 times, right? So we can go ahead and say it's just 3 times 2, so 2 to the 6th power. Or we could also just do order of operations and say that it's 8 squared, because 2 to the third is 8. Either way, we get 64. Okay, next example. Okay, so same idea here as what we did there in yellow on number 1. So a times b to the 5th all over a to the 4th times b to the negative 1. So we're doing our quotient law here. So we're going to match bases. So a, right? And this is a to the first power, of course. So 1 minus 4, that would be a to the negative 3. Okay, and matching the b's again, right? So 5 minus negative 1, that would be b to the 6th. Okay, and then we, of course, have to use reciprocals here for this negative 3 power, right? So this becomes b to the 6th all over a to the negative, whoops, not negative, what's the matter with me? A to the positive 3. Okay, last example. So I've got 3 to the 5th over 3 squared to the negative 2, right? So go ahead and start simplifying. So this is a power to power right here, right? So that's going to be 3 to the negative 4. So I've got 3 to the 5th over 3 to the negative 4. We're going to use the quotient law now. that is going to give me 3 to the 9th, because 5 minus negative 4 is going to give me 5 plus 4, right? And 3 to the 9th power, that would be 19,683. Had to grab my calculator there. Okay, so you're going to see these exact same problems in the actual homework. You need to show your work accordingly. Okay, so into our first EQ and on to the brunt of the lesson. So what is a logarithm, right? So anytime you see a log, right, it's going to be log base B of some number A, right? And we can say that it's equal to C. So an example of that would be log, let's say 100 equals 2, right? And this, of course, would be base 10. Okay, so what I'm saying here is 10 to the second power equals 100. Okay, so I can rewrite this inversely as 10 to the second power is equal to 100. It makes kind of a little triangle there. Okay, and so this is your log function, right? And it's inverse to, so if I rewrote this, right, it would be b to the c power is equal to a. So b to the c power is equal to a, right? This would be an exponential function. Okay? And anytime that you see something, so if you just saw log x, and there's just a blank spot here, there's no number there, it's assumed to be base 10. Okay, so if you saw log 1000, right, there's no base here, so it's assumed to always be 10, unless you do see a number there. Sometimes you will see log base 2, right, of 8, okay, equals 3. Okay, but if there is no base, it's assumed to be 10. So always keep that in mind. So that's cool and everything. We kind of saw like a big time abstract idea of what a logarithm is, but how do they relate to exponential functions? And ultimately here in a second, how are we going to use them algebraically? Right, so we've got an equation, 10 to the x equals 100, right? And analogously, if we had 10 times x equals 100, well, what would we do to solve for x? We would do the inverse of times 10, which is divide by 10. And x would therefore be equal to 10, right? But that's not the case here. It's not 10 times x, it's 10 to the x power. So we need to do the inverse of base 10, okay? And the inverse of that would be log base 10. So if I do log base 10, that's going to cancel with just your exponential base 10. And what you do to one side, you do to the other. So the log and the base 10 cancel, right? Because I did log base 10, that leaves me with x. What I do to one side, I do to the other, right? And log base 10 of 100, so we saw that here on this last slide. If I have log base 10 of 100, that's going to be equal to 2 because 10 to the second power equals 100. Okay, so pretty straightforward, right? And even without using a logarithm, we could have just used common sense. We could have just said 10 to what power equals 100. Well, obviously, x is going to equal 2, right? But using algebra, we said log base 10 of both sides, right? X equals log of 100. Obviously, that's going to be 2 also, okay? Now, like I tell you, common sense isn't always enough. In fact, it's rare that it is. So it's good that we know these basic algebraic rules about this, right? So really quickly, and I don't know why that just happened. Okay, so really quickly, let's look at the graphs of these two functions here. Right, so, well, if my link will work. So let's look at our graphs for these two functions and just so I can prove to you that they are in fact inverses. So let's graph f and g. Okay, so f is an exponential function, like you've already seen, whose base is 10, right? Just a parent function, base 10 to the x power. Okay, g of x, let's see what that looks like. So g of x is going to be log of x, right? And let me change colors here. I don't know why Desmos thinks, oh, that's a good idea to make everything the same color. Okay, and if I do, okay, so we see clear symmetry here. And once again, Desmos is stupid and makes everything the same color. Okay, so we see clearly here, right, that our exponential function and our logarithmic function have a very clear symmetry about y equals x. Okay, this is graphically indicative that f and g in this case are both inverses, meaning, right, b to the x is inverse of log base b of x, okay, as long as the bases match, right? So this log right here was base 10, and so is this exponential function. Okay, so they are inverses, right? And we'll learn more about that in the next lesson. Right now, we're more concerned with the laws of logarithms, or the properties of them, right? And let me switch colors here. I'm getting tired of that. Okay, so evaluate each logarithm. Okay, and you can actually throw these in the calculator too, but we need to know how they work algebraically because we're going to get ugly things like this, right? So we've got log base 10, because there's no base here, so we assume it's base 10. Log base 10 of 10 to the 5th power. Well, 10 to the 5th power, that's going to be a 1 with 5 zeros. So that's 100,000. So we're looking at log base 10 of 100,000. Okay, so we're saying 10 to what power? 10 to what power equals 100,000? Well, our answer here would, of course, be 5. I mean, it's a dead giveaway. It's right there. 10 to the 5th power equals 100,000. Okay, let's look at the second example, and you're going to notice a very clear pattern here. Okay, so log base 10, right? There's no base, so we assume it's base 10. So log base 10 of 10 squared. Well, 10 squared is just 100, a 1 with 2 zeros, right? And we know it's log base 10, so we're saying again, 10 to what power? 10 to what power gives us 100? And again, the dead giveaway is there with that exponent. Okay, so that would just be 10 to the 2nd power, right? So x is very obviously 2. Okay, and here we see pretty much the same numbers, right? Here on example 3. Okay, so log of 100,000, well, we already saw that that's 5, right? So here we're going to go ahead and say that it's simply 5. Okay, and over here, log of 100, well, we already saw, because log of 10 squared is the same thing as log of 100, we're going to get 2 for our answer. So this is just going to be 2. Okay, so log of 100 equals 2. And I should go ahead and iterate that. Sometimes I take for granted certain things that seem obvious. Okay, so now, how on earth are we going to mess with this guy here, number 5? Okay, so how can we rewrite this as an exponential function instead? So I've got log base 10, log base 10 of x is equal to y. And again, we're just going to follow like what we saw over here. We're saying 10 to what power equals x. So 10 to the y is going to be equal to x. Okay, so this is how we would quote-unquote solve it, right? It just depends on what you're given, okay? And so before we move on, okay, I just want to go ahead and say, right, how can we express this as a law of logarithms? Okay, so what it ends up being, and let me go back here in yellow, if I've got log base 10 of log base 10 of 10 to the 5th power. This is the same thing as 5 times log base 10 of 10 to the 1st power. Okay, so just looking at this, that's just going to be 1, because 10 to what power gives you 10? 1. 5 times 1 is 5. Okay, looking at example 2, okay, and I guess I should go ahead and color code here. So looking at example 2, oh my goodness, I can't even match colors. Looking at example 2, well, we've got log base 10 of 10 squared. Okay, and I can go ahead and say that that guy is equal to 2 times the log of 10 to the 1st power, right? And 10 to what power is going to give me 10? 1. And again, we're going to end up with 2 times 1, which is 2. Did our answers match? Well, in yellow, both times we just got 5. In blue, both times we just got 2. Okay? So the pattern here is the power law. Okay, so let's go back to over here, example 5. Okay, we arrive at the power law of logarithms. So if I have log base x to the y power, I can rewrite that as y times log of x. Okay, these two expressions are equivalent. This is our power rule, or our power law of logarithms. Okay, so on to the product law. So we're going to see a similar pattern here. So right now we're just going to evaluate with a calculator. So we're going to say, and we're not going to mess with the base at all, we're just going to say log of 45. Okay, so this is approximately 1.65. We round to the nearest hundred. This guy here, log of 21, that is approximately 1.32. This guy here, oh, this is a little different. We're adding two different ones together. So log of 9, that's 0.95, and log of 5, that is going to be 0.70. Okay, when we add those two together, we're going to end up with, well, this should look familiar, 1.65. Okay, that's kind of weird. All right, let's look at this next one. So log of 7 plus log of 3. So log of 7, that's 0.85 thereabout, and plus log of 3, 0.48. Okay, when we add those two together, and of course I'm just using the graphing calculator and writing down the decimal estimates. Holy dog crap, we get 1.32. Okay, so what is happening here? What is happening here? So the 1.65s, why did we get the same answer with these two? Well, what is 9 times 5? 9 times 5 is 45. Okay? That pattern continues here and here with the 1.32. What is 7 times 3? Well, that's 21. So we can go ahead and make the generalization. So if I've got log of two numbers being multiplied together, this is equivalent to log of x plus log of y, provided that the bases match, right? And these are both base 10, right? And I should go back and reiterate. So this is also the case here. The bases must match. And it did work over here as well, because both of these had base 10 and understood base 10. Okay, just like these examples here. Okay, so this is my product law. Okay, quotient law, last one. So we've got log of 6. So let's throw that in the calculator. Log of 6 gives me approximately 0.778. I'll go ahead and round it 1,000. Okay, log base 4, or not base 4, log of 4. Log of 4 would be 0.602. Okay, so now let's look at these. So these are a little more complicated. So we're going to have log of 12, and that's going to give me 1.079. And we're going to subtract from that the log of 2, whatever that is, 0.301. Okay, and when I go ahead and subtract those numbers, I'm going to get, well, that should look familiar, 0.778. So here we see another pattern happening, right? See what happens with, should it match here and here? So let's see what happened with log of 8 and log of 2. So I'm going to do log of 8. That's 0.903. And take away from that log of 2 again, which we already know is 0.301 from the last problem over here. Okay, when I subtract those two, I get something familiar, 0.602. Once again, a pattern is arising. Okay, so let me use something that's going to stand out more. So 12 divided by 2 is 6. Okay, and we had our 2 matching here. Fair enough. So 8 divided by 2 is 4. And we had our answers matching here. So what is our generalization? Our generalization, bring this over here, our generalization is we have, if we have log of some number or base of some 2 numbers being divided, right? That's going to be equal to log of the same base of x minus log of the same base y. Okay, this is our quotient law. Okay, so now we're just going to kind of do some algebraic messery to play with these a little bit. So we've got an exponential function, right? An exponential equation, rather. And we're being asked to rewrite them as a logarithmic one. Right, so let's go ahead and do that. So 10 to the 8th is equal to 100 million. Right? Obviously, we know that's true. You can throw that in the calculator, or you can just count the zeros. It'd be 1 with 8 zeros. Okay? But we want to rewrite it as log of something, right? And if we're going to do that, we're going to do the inverse of a base 10 exponential expression, which is a log of base 10. So we're going to say log of base 10 of 10 to the 8th power. Well, that's going to be equal to, what I do one side, I do the other. It's a lot of zeros. Okay? And log base 10, exponential base 10, their inverses, they cancel. That leaves me with 8 equals log of 100 million. Okay, easy peasy. Same idea over here. Okay, I'm going to take the log of both sides, and I'm simply going to go ahead and say that log of 1 million is equal to 6. And if I don't write a base here, again, that just means that it's base 10. Okay, so now we've got just a purely algebraic equation here, right? So I'm going to take the log of both sides, log base 10, right, because it's a base 10 exponential expression. So y is going to equal to log of this same base, which is 10, of x. Right, so all it is just a new concept, not a whole lot of actual math to this, just new concept. And really, even that's not that new, because all of the laws of logarithms are very, very similar to the laws of exponents. All right, so that concludes this video. Okay, a lot of the examples that I did are going to be in the homework, so really hope you're paying attention there. If you have any questions, you guys know what to do. Goodbye.